All right, good morning, everybody. We're going to get started here with the Warren lecture.
Does it work? The microphone, does it work?
It doesn't, it just records.
Oh, okay.
So it is my pleasure to welcome you to the 2016-2017 AEESP Distinguished Lecture as part of the Warren Lecture Series here in the Department of Civil, Environmental, and Geoengineering. This distinguished lecture is supported by the Department of Civil, Environmental, and Geoengineering at the University of Minnesota, as well as by the Association of Environmental Engineering and Science Professors. So we gratefully acknowledge support for this lecture. And a special thank you for people who are coming from out of town to the lecture. Co-hosting institutions, the University of North Dakota State University, the University of Minnesota Duluth, and the University of St. Thomas. So thank you for making the trip to Minneapolis. It is my pleasure to introduce the 2016-2017 Distinguished Lecturer, Professor Menachem Elimelech from Yale University. Professor Elimelech is the Roberto Goizueta Professor at Yale in the Department of Chemical and Environmental Engineering. He received his undergraduate and master's degree at the Hebrew University of Jerusalem and a PhD in environmental engineering from the Johns Hopkins University, working with the late Charles Omilia. He started his academic career at UCLA before moving to Yale University in the late 90s. At Yale, he established the environmental engineering program, and he established a highly renowned research group that specializes in all aspects of membrane materials and processes for water treatment, seawater desalination, and wastewater reuse. He's also an expert in colloid and interface science in aquatic and environmental systems, and also in the environmental applications and implications of nanotechnology. So please join me in welcoming Professor Elimelech.
Thank you. Okay, can you hear me? I know the microphone is only for the recording. So anyway, my pleasure to be here. It's my second time. I was here about 9-10 years ago, according to Paige. And it's always a pleasure to be in this great city. So today I will talk with you. And again, I would like to thank, of course, you for hosting and all the partner institutions, University of North Dakota State, and University of Minnesota Duluth, and another small college? St. Thomas College. Great. So this is my lecture number 14. I have 2 more to go. It was quite a long year. And you see I'm already smiling because I'm seeing the end. But it's fun, really. So today I will talk with you about desalination. And hopefully after presenting some of the information, we will try together to answer, is seawater desalination a sustainable solution for global water scarcity? So the lecture will be more like a big picture thing with some fundamental components. And I hope that if everyone, even if you never heard about membranes, will be able to get the main message of the talk. So I would like to start to tell you where I'm coming from. I'm coming from Yale University, from the Environmental Engineering program. We are part of the Chemical Engineering department. We're quite a small program with 6 core faculty. And we also have some affiliated faculty in the School of Forestry and Environmental Studies. We cover a broad aspects of environmental engineering, water, air, and soil. And we cover it all the way from the molecular level all the way to the system level. Before going to the technical part, I would like really to thank the people who did all the work. I mean, a generation of students and postdocs. And again, I continue to learn from my students and postdocs. And one of them was Santiago all the time. They're really the source of all my knowledge. So really acknowledging them. So I'll start with a slide that most of my talk I studied because, again, it's the global challenges for the new millennium put together by Nobel laureate Richard Smalley. And again, we are not surprised to see that energy and water on the top of the list. Indeed, many of the challenges there are interrelated to or related to water and energy. We can tie together the water and energy in what we call the water-energy nexus, and you will see it during my talk. I will talk about desalination, a way to make water, but you will need a lot of energy to make this water. Similarly, to produce energy, for example, by thermoelectric method, you will need a lot of water. So water and energy are related by the water-energy nexus. We can extend this nexus. Many times we extend it just because the funding agency came up with this coin, and we jump in. we extend it to the water energy food nexus. It's a buzzword, and if you want to get funding, you need to put something in the proposal, water energy food nexus. And the reason is that at least 70% of the water goes to agriculture, and in some developing countries, 90% of the water goes to food and agriculture. So it's quite significant, and this is why we have all these nexus here of the energy, water, food nexus. Water and energy are also related to the United Nations Sustainable Development Goals. These are the goals that are replacing the Millennium Development Goals. Specifically, the challenges that highlighted in red here. We can zoom on them. Zero hunger, clean water, clean energy, and climate change. They're all related to this nexus of water, energy, and food. Now, there is a rapid growth in water consumption all over the world. You see here the graph for the agricultural section, industrial and domestic. I already told you that agriculture consumes most of the water. And you see the projection to the year 2025. We have sort of like exponential growth. And this growth in global water use just follow the growth in population. So I don't have the graph for the population, but they follow roughly the same thing. Now, when you think about water, most of us, again, think about liquid water, but all of us using or eating water because there is virtual water or embedded water for any product. If you drank a cup of coffee today, it took 140 liters of water to produce this cup of coffee. If you will eat lunch and you will eat meat or hamburger, it will be 2,400 liters. Even if you are vegetarian and eat healthy food, you see one head of broccoli will be 5.4 gallons. If you wear leather shoes or anything leather, it consumes a huge amount of water. And the evil of all, if you follow the news in California, is the almond. The almond growers were under attack because one almond consumes 1.1 gallons of water. So with this introduction, I don't need to convince you that there is not enough water. We can get certain amount of water from the hydrological cycle, from river, lakes, but it's not enough. So the question is, how to increase available water supply beyond what we can get from the hydrological cycle? And this we do by engineering. Again, this is where engineering jump in. You can either desalinate seawater that otherwise you cannot drink, or reuse municipal water. And my talk will focus on desalination, mostly only seawater desalination. And there is a critical need to enhance the sustainability of desalination. And this is what I will focus on. So let's just talk about a few features of desalination. In principle, desalination offers an unlimited amount of water. The ocean is vast, and you will never deplete the ocean. Again, as much as you take, it will be enough. Indeed, I was reviewing a paper that suggested many desalination plants that you desalinate water, then store it in aquifer is a way to prevent ocean rise. But once you do some calculation, you need to have desalination plant everywhere. And of course, I rejected the paper. So it's not, it's not. So production of fresh water without impairing the natural ecosystem. We need a lot of water for a healthy ecosystem. And when we take water from river and lakes, but here if you take from the ocean, it will not affect the ecosystem. However, it's more energy intensive. I will spend a lot of time on energy. It's roughly between 3 and 5 times more energy than treating the water from, where do you get the water here? From the river, Mississippi River? So at least 3 to 5 times more. And also there are concerns about the potential environmental impacts of desalination that I'm going to describe. So the key process for seawater desalination is reverse osmosis technology. Although there are some other technologies old in the Gulf countries that involve thermal desalination, they are very energy intensive. So the state of the art is reverse osmosis technology. For those of you who never heard about reverse osmosis, I would like to guide you. You have an intake of water from the ocean. You have a pre-treatment stage similar to the way we treat water for drinking water supply, more physical and chemical processes. We have the reverse osmosis stage that does the actual desalination. And then we have a post-treatment to add minerals and sometimes to remove some other things that are not removed by reverse osmosis. Roughly, you can see here the thickness of the line is proportional to the energy consumption. And not surprising, the reverse osmosis stage will consume most energy, and we will spend a lot of time on it. Now, as I told you, desalination is becoming popular. There are many desalination plants built all over the world, and I'll give you a few examples. In California, after 12 years of deliberation, discussion, fighting with environmental groups, eventually they built a plant a year ago and in Carlsbad, next to San Diego, and it's 70 million cubic meter per year. Israel completed 5 major desalination plants. These are 2 examples, and are going to build a 6th one. And each one of them is twice as much as the one in San Diego. Just to give you the scale, in Israel, I mean, the Mediterranean is very, very, very small. It's probably like the distance from, outside the Mediterranean, from San Diego to Santa Barbara, probably. Okay, so to answer the question if seawater desalination is sustainable, I will go through 4 major questions and give you the technical details, and hopefully they will help us to answer this question. Specifically, I will talk about the energy efficiency of desalination, give you some of the real values. Then I will talk about materials. Will materials be able to really reduce the energy consumption? Then about other technologies. Again, I mentioned that reverse osmosis is the gold standard, but maybe there are some radical technology that will reduce the energy. And then I will talk about the environmental impact of desalination. So let's start with question number 1. What is the current energy efficiency? If you talk to the average person in the street and so on, you talk about desalination, wow, it's energy intensive. So let's give you the numbers. Let's define what is the minimum energy for desalination, and you go to thermodynamic, assume a reversible thermodynamic process. So this will give you the minimum energy that you will never be able to do less than it. And it's independent of the technology, because this is thermodynamics. You can, many ways to derive it. If you take any basic chemical engineering class, the easiest way to calculate the delta G of separation or delta G of mixing, which is, again, just minus. And when you do the calculation for 35 grams per liter, if you just take 1 drop of water, which we call zero recovery, just little water, you need 0.76 kilowatt hour per cubic meter. In desalination, we squeeze more water. We squeeze about so we can get half of the seawater become fresh water and half become concentrated brine. And this is what we call 50% recovery, and we will need 1.06 kilowatt hour per cubic meter or 1,000 liters of water. Now, many of us can imagine what is 1.1 kilowatt hour, but I would like to give you just a tangible example. I don't know how many of you remember these incandescent, light bulbs that have 100 watts. I mean, at least some of the older ones here. If you take 1,100 watt light bulbs and turn them on for 1 hour, this will be the electricity equivalent to produce 1,000 liters of water or 2,000 bottles of water of half liter each, just to get an order of magnitude. Now, when you look at this energy, the way we operate reverse osmosis, the membranes are packed in a module, and you have 6 modules in series, about 6 meters long. The water enter here, the seawater, and then as you move, you squeeze fresh water, and then the salinity of the brine that's moving here increases, as you see here. This is what you enter. This is the salinity or the osmotic pressure. Again, they're related when you exit the module. So the area under the osmotic pressure curve is exactly the Gibbs free energy of separation based on a reversible thermodynamic process. This is the 1.06 for 50% recovery. And anything above, these are the irreversible losses. Now, you see that to operate reverse osmosis, because of the membrane area and the modules, we need to apply pressure which is at least equal to the osmotic pressure of the exit brine, because otherwise we will not get water going through. We need to overcome the osmotic pressure. So because we need to operate at this pressure, we can define now a practical minimum energy, which is simply equivalent to this pressure here. If you have seawater, which is about 27 bar or atmosphere, 50% recovery, this would be 54 bar. And if you convert the unit for 54 bar per cubic meter, you will get 1.56 kilowatt hour per cubic meter. This assuming that all the pumps and everything ideal. So the way we operate reverse osmosis nowadays with fixed pressure, you cannot do it with less than 1.56 kilowatt hour per cubic meter. Now let's see what's happened in the past 40 years since the reverse osmosis technology was invented in the 70s. we see this is the energy consumption, a dramatic decrease in energy. And although I do not present any data here, it's just the data that we have now, it doesn't change, it's fixed here. Now, why we got this energy decrease in the energy consumption? We have better membranes. Indeed, the membranes, initial one were cellulose acetate membrane. And in the 80s, not far from Minneapolis, the thin film composite polyamide membrane was developed, so it reduced dramatically the energy. We now use pressure exchangers that you can recover all the pressure in the brine. In the past, they were discharging the brine with all the pressure, and you have better pumps and so on. Now, I can tell you that in the past 10 years, there were no change in the energy consumption. And this is here. The best reverse osmosis plant, just the reverse osmosis stage, does it with about 2 kilowatt-hour per cubic meter. I told you that the 1.56 is the practical minimum. You can never do it better. And 1.06 is the energy for a reversible thermodynamic process, which is not practical. We can find some way to do it better than the 1.56, and I will talk about it later. So you see, nowadays, the way we operate reverse osmosis, you have a room for about 20% improvement. So you cannot have any dramatic changes in the energy consumption that will completely reduce it by a larger factor. Now I can tell you, just conclude the energy part, that the entire plant consumes most of the time 3. Again, just the reverse osmosis stage 2. And sometimes you can go all the way to 4, and this sometimes mostly in Israel, because in Israel they use all the water for irrigation, and although they do not use directly seawater desalinated water for irrigation, it goes to drinking water. It's become wastewater, and all the wastewater in Israel is used for agriculture. And what they do in Israel, because reverse osmosis stage do not remove boron effectively. Boron is uncharged, low molecular weight, and anything that is neutral can go through the reverse osmosis relatively easily. So in Israel, they had another 3 stages of reverse osmosis just to remove the boron. So eventually, when they get the wastewater, it will not have high level of borons, because many crops in agriculture are more sensitive to boron than humans. Indeed, the regulation for many crops are lower tolerance level than for human health. Okay, so this is question number 1. Now let's go to question number 2. Can novel materials reduce the energy consumption? And this is where material scientists jump into it. It's another room for getting more proposals, more ideas, and so on. And they jump in a way they went through high permeability membrane, or high flux membrane. And they promise a quantum leap in desalination. And the rationale for them, many physicists, some of them are brilliant and so on, they were just thinking, the energy consumption in reverse osmosis is by pressure, because of the pressure. If we can have membrane with lower permeability, higher permeability or lower resistance, you need less pressure. And if you need less pressure, you need less energy. So there were a lot of studies on this. And they were published in very high impact journals, in Science, in Nature, and so on. One of them was carbon nanotubes. We know that carbon nanotubes, water flow very, very high flow rate, about 10,000 times more faster than what you calculate based on just fluid mechanics, mainly because it's hydrophobic and smooth. It's more like flowing like a file of molecules. There were aquaporin. These are the water channels that we have in cells of living organisms and plants that can transport water at high rate. And more recently, graphene. Graphene is a 1-atom thick, two-dimensional material. And they saw that if you punch the right hole, because it's very, very thin, the resistance will be very low, and you can get a lot of energy savings. Now, whenever you publish in these high-impact journals, immediately some, media come in, radio, and so on. And I don't know how many of you have seen the John Oliver, how the media turns scientific studies into morning show gossip. Maybe nowadays we call it fake news. So I would like to show you something that really happened for the graphene. Lockheed Martin, again, it's a good company. They know thermodynamics and everything. But they published something or did some molecular dynamic simulation. And they say if we take two-dimensional graphene, have some holes there, we can get fluxes which are 500 times higher than current membranes. What the media did, it's propagate. The media claimed you can use 99% less energy than current things. And probably they don't know thermodynamics and so on. So this is the way sometimes the media, and again, we see all this many times, at least in this field, inverse correlation between the impact of the journal that you publish and the practicality. So whenever you see anything in Science and Nature, it's good for the PI, good to get tenure, but probably will never make it to the market. But all the young faculty publish in Science and Nature. It's good. So, but I already told you that the energy in desalination, it's more thermodynamic control. It's not more like the rate control separation. The membrane resistance doesn't play an important role because the osmotic pressure governs it, because we need to operate at least at this osmotic pressure, which I told you it's already 1.56 kilowatt-hour per cubic meter. In reality, we apply 10 to 20% more because we have pressure drop as the water flow in the module. We have concentration polarization. And the current polyamide membrane that were developed here not far from Minneapolis just work in this range. They're good enough. We work in this pressure, and it works very well. Now, we have done also more rigorous thermodynamic full-scale modeling of the process with all the losses and everything. And we have shown it rigorously rather than the semi-quantitative way I showed you earlier. Let's focus only on the seawater. This is the energy consumption kilowatt-hour per cubic meter. This is the water permeability. Current polyamide membrane, the permeability is between 2 and 3 LMH per bar. And you see that beyond this limit, there is no improvement in the energy consumption. Earlier, when reverse osmosis was established, cellulose acetate had a very, very low permeability, and then we were in this range. So this is why we had very, very high energy consumption. Now, let's look more about the materials, and specifically about the current membrane, the polyamide membrane that was developed again in the, I think, early 80s. And it's the gold standard, but it's prone to fouling because of these reasons. It's relatively hydrophobic. Polyamide is hydrophobic. It has a rough surface because of the interfacial polymerization process. It contains carboxyl group. Also, it's very sensitive to oxidants. You cannot rinse the membrane with chlorine and kill the biofilm because the polyamide will degrade. And all these properties make it, the membrane, very prone to fouling. And what I will argue that really to improve the energy efficiency and the performance of reverse osmosis, we need to develop fouling resistance membrane. This will be always the case. We always need fouling resistant membranes. And this will improve the reliability. You will use less chemicals for cleaning. And also you'll save some energy because nowadays when you get fouling, the resistance increases dramatically. So what they do in the desalination plant, they increase the pressure so they can maintain the same product water coming out of the plant. And by raising the pressure, you will have more energy. And I would like now just to show you a few things that we are doing in our lab to improve the fouling resistance of this polyamide. Again, polyamide is hydrophobic. A lot of organic matter in water, hydrophobic, like to stick to the membrane and cause fouling. So fouling, when you have this organic matter accumulate and interfere and add more resistance to flow of water through the membrane. And I would like to show you a recent paper that we just published of increasing the hydrophilicity of the membrane by using Zwitter ionic polymer brush layer. Zwitter ionic polymers are polymers with a positive and negative group next to each other. And we know that such functional groups can absorb a lot of water molecules. So we said we can graft this polymer brush layer on the membrane. This brush layer will absorb a lot of water molecules, very thick hydration layer. And whenever you have any organic foulant, to really attach to the membrane, you need to displace the water, which is energetically not favorable. And this is the way you provide more like steric barrier. So we take, this is an example, a monomer of sulfobate-10 methacrylate. We use ATRP. It's a well-known technique to control technique to grow the brush layer to the thickness that you want. We bind the initiator for this process through polydopamine chemistry, a well-known chemistry. And you can control the thickness of the brush layer of the polymer, and you can get brush layers of polymer with a sulfobate-10 methacrylate. So this is the contact angle before. This is the contact angle after the modification. The contact angle decreases. And we wanted to see how it improved the fouling resistance. So first, we measure the fouling tendency by atomic force microscopy. Again, Santiago is one of the experts in this area. You can take a particle probe, coat the particle with the foulant of interest, let's see, organic matter, glue the particle to the AFM tip, and you bring the particle coated with the foulant to the membrane, and you measure what force needed to remove or pull off the probe. If the membrane is sticky and things like to foul the membrane, you need some force to remove it. If the membrane is anti-fouling, the foulant will not stick and there will be no force. And we measure these events, many, many measurements here. If it's negative, it means it's sticky. You see the control membrane, many, many sticky events, and they're quite large. I mean, you know, the units will not tell you much, but those of you who work in this area. So a lot of sticky events. The modified membrane, we saw very little sticky events, and most of them were non-sticky, which gave us indication that indeed we made a membrane that may be fouling resistant. Then we do experiments here, simple experiment like static adsorption test, in which you take the membrane, dip it in a protein solution, and you label the protein with green fluorescence. So after 1 hour, you remove it, rinse it. If the protein stuck to the membrane, you will see green, as we see here. And indeed, because the control membrane was not fouling resistant, the protein stuck very, very effectively. The modified membrane, which we already predicted, there will be very, very sticky events by AFM. Nothing, I mean, you can see some green, it's hard to see it here, but almost none of the proteins stuck to the membrane because of this hydrophilic brush layer that we have on the membrane. We can also do the usual test that you do in a small membrane unit in the laboratory and measure the water flux decline as a function of time, or the volume of water that comes from the unit. And you see the control membrane, a lot of flux decline, and the modified membrane, less flux decline. And these are conditions that we have done in very, very, very high organic matter. You will never find any water like this. This should be almost like sludge, just to accelerate the fouling test. We also do some work with graphene oxide. We found that graphene oxide is antimicrobial, can kill microbes. So we develop a way to bind the graphene oxide to the membrane. Then you can get these graphene oxide nanoblades, more like that can kill the microbes by combination of physical and chemical oxidation mechanisms. Now let's go through the detail. The membrane has carboxyl group, which are not good, but they are part of the interfacial polymerization. So we can activate this carboxyl group by the well-known EDC NHS chemistry. We get a reactive ester, and we bind ethylene diamine here. We activate the graphene oxide sheets also the same way. They have a carboxyl group. We activate them, and then this reactive ester will react very, very fast, and we can get this graphene oxide covalently bounded to the surface. This is the membrane, the control membrane, typical rough membrane for polyamide. And this is the graphene oxide membrane that you bound the graphene oxide by covalent bonding. See some of the color. In any modification technique for fouling resistance, it's key not to affect the water permeability and the salt permeability of the membrane. You want the membrane to be permeable and highly selective. And indeed, we see that when we measure the water permeability coefficient and salt permeability coefficient, the control and the graphene oxide modified membrane have the same values, roughly. And then we put some bacteria on the control membrane. So 100%, it means that all the bacteria are alive. And this is the bacteria on the graphene oxide modified membrane. Only 40% of them were alive. You can look at this membrane. This is the control membrane. This is typical bacteria, which is healthy, round, and so on. And this is the bacteria after contact with the graphene oxide. It was very, very severe damage to the bacteria wall. They shrunk, and they practically died. So, and we also did some biofouling tests. We were able to show reduced biofouling, but you cannot minimize biofouling. Biofouling always occurs. As long as you slow it down, you can really save a lot of energy and money. It's impossible. Bacteria, again, there are some microbiologists, bacteria always win. You just need to slow them down and not work as fast. Okay, question number 3. Are there any other systems of technology that can reduce the energy consumption? I can tell you that reverse osmosis technology is still the gold standard. You can review some papers and hear people calling me, I've invented a new technique and so on. But for the large-scale desalination, there is nothing better than reverse osmosis at this stage. Remember this minimum energy, the osmotic pressure curve, and the area above it, which are the irreversible losses. I will show you, and this is very well known from chemical engineers, do staging all the time. It's what you do in studying in undergrad. And I can show you some way that you can reduce the energy. It's not exciting like carbon nanotube and so on, and I do not recommend assistant professor to work on this process modeling, at least in environmental engineering. But I can show you that you can, again, I can probably, I already have tenure. So I'll show you a very simple case. If you just do 2 stages, you take the brine from the first stage and have another pump and push it through another stage, you can go from the practical minimum energy of 1.56 to 1.28. Dramatic change by very, very simple. And you can see it schematically because the first pump will just go up to here, recovery equivalent to here, and the second pump will achieve the other recovery, and this is the area that you will save, the energy that you will save. Membrane companies know about it. They can do it. We in academia think only about energy. For them, the most important is the cost of water. By having 2 stages, the capital cost increases, and you will increase sort of the cost of the process, so they do not go with it. Although it will save energy, they still do it in 1 stage for seawater desalination. Now, you can analyze these things mathematically. Again, multi-stage. And when you analyze it mathematically for the multi-stage, many of them, when you go to infinite stages, mathematically here you can do it, you recover exactly the same expression that we developed from the Gibbs free energy of mixing, or anyway for the minimum energy of desalination. For infinite stages, this is exactly 1.06 kilowatt hour per cubic meter. We get the same expression, again, not surprising. And again, but no one will beat infinite stages. I mean, even 2 stages we do not build. So the question is, we have physical stages, and they increase the capital cost. Can we think about a different way that you will have operational stages rather than physical stages, and try to be close to the osmotic pressure curve? Because if you ride on the osmotic pressure curve, you will achieve the reversible minimum energy. So there is a company in Israel, a startup company, that quite doing very well now in brackish water desalination. They developed the closed-circuit desalination. And these will have stages which are operational. You will have only 1 stage, but we'll do operational, and I'll explain to you. If you have the seawater coming here, you operate at a certain pressure, and then you circulate the water, and then as permeate water, fresh water coming here, the salinity will increase until the salinity and the osmotic pressure reach close to the pressure that you apply. Then you go to the second stage. You increase the hydraulic pressure and continue to circulate. The osmotic pressure increase, and you go another way. So these are operational stages, and we analyze it. You will never approach the reversible, the minimum energy of a reversible thermodynamic process, because always you have here feed water that mix here with the brine. And whenever you have mixing, is an increase in entropy. But we get relatively very close to some degree to the minimum energy. And I will show you some of the calculations. Again, these are very simple process engineering. You can achieve dramatic energy saving, much more than all these carbon nanotube and aqua pouring that people promise and publish in Nature and Science. But it's very, 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 very important. So let's assume that 1 stage, this is 100% is just the way we operate reverse osmosis, 1 stage. If you do 2 operational stages by this closed-circuit desalination, you will save 12% energy. If you will do 4 stages, 18, and if you do 8 stages, 22%. And these are very practical ways. They can achieve 20% energy, which is dramatic. So question number 4, what are the environmental impacts of seawater desalination? To remind you, the interaction of the desalination plant with the environment, we have intake, we have energy that you produce, you have greenhouse gas emission, we have discharge. I did not show you earlier. You discharge the brine. So roughly, when you think about the environmental impact, the first one is impingement and entrainment, was a term invented by California, because when you suck the water from the sea, there is a screen, and you can retain some larvae and some other organisms. And what they do in California now, they are not allowed to take the water directly from the ocean. They dig a well in the dunes next to the ocean, and the water will go through the dunes to the desalination plant. So you prevent this screen. You will have greenhouse gas emission, I'm going to talk to you about very soon. And you will have brine discharge to the ocean. It's twice as much concentrated. It's, again, with some maybe few cleaning chemicals. But, again, you need to discharge it in the right location, the place that you have enough mixing. And this is an area that we need to have more long-term studies. I wonder, with the 6 major desalination plants in Israel, what will happen 10 years from now to the coastal area with all the brines that are going there. So what I would like is now just to focus on the greenhouse gas emission. Give you some typical values. This is the range of energy for typical existing desalination plants. We know also that for 1 cubic meter, we know how much energy, and we know how much CO2 we need to get this energy. So the calculations show you will have 1.6 kilograms CO2 per cubic meter of fresh water per 1,000 liter. If you take Israel with 0.65 billion cubic meter per year, it will be 2,600 gigawatt hour per year, or 1 billion kilograms CO2 per year. Does it tell you anything? I mean, it's hard to imagine, but let's give you a back of the envelope calculation. If you take a typical cars, let's say mid-sized cars, this CO2 is equivalent to adding 250,000 cars to the roads, whatever, in Israel. 250,000 of cars, just equivalent of the CO2. Now, let's give you more feeling about this energy, because you know, the numbers do not say much. And let's give you some examples for, let's assume a good desalination plant with 3.5 kilowatt hour per cubic meter. I think this is the one maybe in California or some in Israel. In California, for Southern California, they bring all the water from Lake Shasta and going through the Tehachapi Mountains for the pumps all the way to Southern California. Just to bring the water through this aqueduct, you will need 2.3 kilowatt hour per cubic meter, already close to the reverse osmosis. And once you treat it, it will be roughly about the same. They also get water from the Colorado River, which is closer, and it's 1.6 kilowatt hour per cubic meter. Let's give you more tangible examples. To get 1 cubic meter of water, you can burn certain oil to get the electricity. And the calculation shows you need about 0.6 kilogram oil to get 1 cubic meter or 1,000 liter of water through desalination. This is the oil that you need to produce the energy. If you drive a car, to this oil to get 1,000 liters is equivalent only to driving 2 to 9 kilometers in the 2 to 9 kilometers, how much is 5 miles? Many of you us drove to work at least 5 miles. So whenever you drive, just think how many thousands of liters of water you can produce. Also, to get 1 cubic meter of water, it's equivalent only to having an air condition in a room, small room, for 1.4 hours. How many of us that travel a lot to conferences and going to the hotel at midnight, get to the room is freezing 60 degrees, we're turning on the air conditioner from the morning. So imagine how much water we can desalinate. Okay, this was question number 4. Now let's go to what's next, what the next generation membranes, what are my vision, and then answer the question, is seawater desalination sustainable or not? I think, okay, with time, okay, good. So I was told that I need 45 minutes to be 48 maybe. Okay, the current membranes, reverse osmosis, or even other ones, but let's focus on the reverse osmosis, are constrained by what we call the permeability selectivity trade-off. It's an inherent limitation that you cannot overcome. And this limitation tells you that this is the salt permeability, this is the water permeability, and the experimental data that we have here follows here, which tells you if you want to have a membrane with lower salt permeability, because we need to remove more boron, for example, and the membrane companies can tweak the membranes so they can get 95% of boron, but because they reduce the salt permeability, also the water permeability will be very, very, very low, and then you will need a lot of energy. So you cannot, at the same time, decrease the salt permeability and maintain the water permeability. So the water permeability also will decrease. Or in other end, if you also want to get higher water permeability, also more salt will go through the membrane. This is really an inherent limitation, and we need to think now about a completely new paradigm that overcomes this permeability selectivity trade-off. It's a long-standing trade-off that many people try by other ways, and especially in the gas separation, and we don't have a solution to it. You can take the data that I showed you here and plot it in a way that's more common in the gas separation. I know there are many people here in the chemical engineering that do, world expert in gas separations. Instead of the salt permeability, you present water permeability over the salt permeability. Again, and I will call it water-salt selectivity. How selective is the membrane to let water go through? As a function of water permeability, and you will fall, this is the data I showed you earlier, and these are some other data from polymeric materials. Making some calculation where they fall. And roughly, the most extreme data that in a polymer you get here. So this is what you call the upper bound. Current membranes are roughly in this location, the current TFC membrane. So the question, if we need to have next generation membrane, should I increase both the water-salt selectivity and water permeability? Should I increase only water permeability, or should I increase only salt selectivity? So we analyzed this idea in a recent paper in ES&T Letters. And we've shown, and I showed you earlier here, that there is no impact if you increase the water permeability. I show you it doesn't increase the energy consumption. It doesn't reduce the energy consumption. It doesn't have any impact above roughly 2 LMH per bar. And what we argue, and we gave a lot of examples and calculation, that you really need to think about the increased selectivity. If you have a very highly selective membrane, you will not need to have another 1, 2, or 3 passes to remove boron. These membranes are also used for wastewater reuse. And many of the trace organic in wastewater go through the reverse osmosis because they are low molecular weight and uncharged. Imagine if we have a very highly selective membrane, we can solve this problem, and many other things that we discuss in this paper. So what I would like now is just to talk, what I think, and we summarize it in a recent invited review article. What are the next generation membrane? In my opinion, they should be highly selective, and membranes that operate in such a way different than the current membranes that operate based on the solution diffusion mechanism. This solution diffusion mechanism bound you to this permeability selectivity trade-off. And we discussed aquaporin membranes and carbon nanotube that earlier, 10 years ago, and even now you can see some papers, we're still trying to push it for high water permeability, and I showed you it's not important. We also discussed synthetically designed channels that you can design the channels and incorporate them in some impermeable matrix. Not easy, it's mostly by self-assembly. And also we discussed some small molecules like surfactants or liquid crystal that you can bottom-up approaches, assemble them, and create these pores of 1 nanometer range, and that can hopefully will achieve desalination. So here also we discussed graphene oxide. People suggested graphene oxide by putting these layers of graphene oxide, mostly because the Nobel laureate Game suggested it. It will never work. But we discussed it in the paper and so on. So here I would like just to highlight just these 2 membranes and how they can improve the selectivity. Again, this one also we have ongoing work, and we have some success here to get 1 nanometer pores, but we do not see anything going through the membrane yet. So let's start with the aquaporin. Aquaporin is an amazing water channel, and some aquaporins can in principle remove all solutes and let only water go through. In this paper, they discuss the mechanism, and this is more like the channel with our glass shape. In the middle, there is the right diameter and the right functional groups, that the solute have some interaction here. And what they found, the way you control the solute, if they're big enough like urea, it will retain by size. But the small solutes, ammonia and oxygen, because of the interaction, when the interactions are more hydrophobic, the energy to pass through this opening is high, and you can retain even ammonia and oxygen. So they found an inverse correlation to the hydrophobicity and how easy the molecules will pass through the membrane. Now imagine if we can get these aquaporins and incorporate them into a membrane. So the current state of knowledge at this stage is only we can incorporate this aquaporins in vesicles of either lipid bilayer or black copolymers. And you can show that you can get some water going through and solute. And, so some promise. The key, and this will be very, very challenging, is how to incorporate the aquaporins in a planar membrane. This should be done by more like self-assembly and so on. But the key here that we need to have the aquaporins well incorporated, and we need the other layer that you incorporate to be completely impermeable, and it's challenging. It may be impermeable for water, but some of the organic solids like to absorb into this lipid bilayer and can go through. So we are doing some work here, and hopefully we'll come up with some results, theoretical and then experimental. But this is the main challenge. I mean, I guess we are now at least 5 to 10 years far from here. But the key for the aquaporins, the removal mechanism is different than the solution diffusion mechanism, and this is why you can overcome this permeability selectivity trade-off. The last one that I'm going to describe is carbon nanotubes. And again, they were shown earlier to get high water permeability. But imagine that if you can get this carbon nanotube, we will take single-wall carbon nanotube of diameter less than 0.8. So it can remove all the ions at least. And if you can find some way to pre-select the right carbon nanotubes and incorporate them into a polymeric matrix and align them. And this is an ongoing work. I mean, work that we have done, mostly collaborative with Shinidu Mosuji in our lab. This was his work with my student Megan Mauder. And we found some way that we can get some mesophases, and that you can self-assemble into some structures, hexagonal structures. And you can sequester this carbon nanotube in this aqueous channel in between these hexagonal mesophases. And we choose the right mesophase that you can also polymerize. So what we do, we sequester the carbon nanotube, then we use magnetic alignment. So the carbon nanotubes are aligned through the alignment of the mesophases. And then you polymerize it and you lock the structure. We were able to show it. We can quantify the density of the carbon nanotube, but unfortunately, nothing went through the carbon nanotube because it was impossible through this process to keep them open. And again, I mentioned earlier some other approaches that I showed you here. What we are trying now to take some liquid crystal surfactants and create the pores and without incorporating any carbon nanotube and have the pores as the channels for water permeation. We were able to get a pore up to 1 nanometer, but again, we show some ionic conductance, but water did not go through, and even gas did not go through. So whatever it looks like 1 nanometer, probably it's not open enough, and we're trying to find some way to open it. So to conclude now with the question, is seawater desalination a sustainable solution? I provided you enough technical information, and hopefully those of you who never heard about desalination can get a better feeling about it. And these are the conclusions that we have in the outlook of our review article. So we know that there are many other options to get water. For example, you can reuse wastewater. You have conservation and so on. So this is what I mentioned here. Although several options currently exist to augment freshwater supply, including treatment of low-quality water, water recycling and reuse, these options alone will not be enough to meet the current need. Even if you reuse the wastewater, it's not enough. So this is statement number one. And there is a big push in many countries, and especially in California, to reuse wastewater and have it for direct potable use, that you just treat the wastewater and immediately get it to the distribution system. And roughly, I did not mention it, the total energy of this reuse process for wastewater is to be about 1 kilowatt hour per cubic meter, much less than the desalination. So we need to push it. But even if you do it, it's still not enough. We still need more water worldwide. Secondly, while seawater desalination must be considered after all other options have been implemented, and this is what we discuss in this article, you need to try all other options, but use desalination as a last resort, but regardless, it must be considered as a crucial component of the portfolio for water supply options. In any water supply, like the way you invest in anything, you need a portfolio. If you have a dry, semi-arid region, some of it will come from groundwater, some of it will come from wastewater reuse, and some of it can come from desalination. So it's not bad, and I gave you some value of the energy. Imagine if you drive 5 miles, you could have produced 1,000 liters of water. So just to tell you the order of magnitude, or if you turn off the air condition for 1 hour, you will get enough water. And lastly, for water scarce countries that already implemented all other options, and this is what they do in the Gulf countries in Israel, desalination may serve as the only viable means to provide water supply. So we give a legitimate way that if you try all other options, you can use desalination despite the cries of the environmentalists in California and all kind of things. So, unless you don't want to expand and grow. So lastly, I would like to thank the funding agency, the groups, and is Santiago here? I didn't pay attention, no. Are you here, Santiago? Oh, I should have a better picture that you're here. When you give, huh?
I am there in the one that says Elimelech lab.
Okay, good. Okay, so I mean, I always make sure that whenever I go, if I have any of my students or postdocs, to show the picture. So anyway, I hope that I provide you enough technical details. I told you what's my opinion about water scarcity, and I'll be very pleased to answer any questions that you have or any challenges. Now, one thing to qualifying, I use sustainability here in a very, very loose way. I know nothing about the super way you define sustainability, but I think you understand what I mean. Thank you very much.
So before starting the Q&A session, just an announcement. We'll be having a poster session at 2 p.m. outside in the rotunda with various research groups from the university as well as from the co-hosting institutions. So please join us for that at 2 p.m. Tea and scones will be served. And one more thing, before asking the question, please wait to be handed the microphone because this is being recorded for folks following outside of the university. So any questions for Manny?
We always need the first one to ask, and then all the questions comes. Okay.
Thank you. So it seems that given the position of these countries where they use desalination, it would be convenient to integrate that with solar power. How many solar panels or how much of an area would be required to support a desalination plant of this size?
Any renewable energy like solar and wind, you cannot use it directly because it fluctuates. So what you do, you just need to feed it to the grid. And once you feed it to the grid, I mean, it will be electricity, whatever the calculation that we have shown here. In Perth, Australia, they advertise it that they use wind farm and it's all renewable energy. But what they do, the wind farm, which is far away, just feed it to the grid, and then they use it as electricity. I mean, I think in this article we argue, and some maybe not in this article, that to enhance sustainability, every utility that wants to build desalination plant also built an equivalent farm of renewable energy to feed the grid. So this is sort of like the answer. Ideally, in the future, if everything would be solar and it would be very, very cheap, desalination would be just a trivial.
Thanks.
I'm thinking about the supply-demand curves that exist for water.
Okay.
And I don't know what assumptions you made in terms of water use and water need, but when water becomes more expensive, wouldn't the supply-demand curve tell us that we use less water?
Okay.
And can that go? How far will that go to solve the water problem?
So just to increase the cost of water?
Yes.
You think people will agree to it? I mean, imagine if you try to increase even by 1 cent the gas tax, so you'll be better education. I mean,
they may have no choice.
Yeah. I mean, part of the measures, in some countries, I mean, in Netherlands, they pay close to €2 per 1,000 liters of water, the water bill. And I agree that this is the way, but again, it's beyond the scope of my talk and my expertise. You're a water resources guy, no?
Yes.
Okay. So I did not talk about, the only thing that closer water we can think about is conjunctive use, portfolio for water supply. But I agree with you, if you increase the cost, of course, they will be using less water, and maybe you need less desalination.
Okay.
But it's hard to implement it.
Yeah, okay.
Thank you. So one of the things with the water scarcity as well is that some of the countries that are going to be hit hardest by water scarcity are poor developing countries. So particularly parts of Africa.
Yeah.
So the existing membrane technology is sometimes difficult enough to make on a cheap basis. Do you think the sort of future membranes are technologies that might be available to those developing countries, or do you think they may have to go a different way?
I mean, for developing countries, I mean, I would not recommend to go to desalination. They should try all other options, and there are some technologies which are manageable and so on. I mean, I cannot see how desalination can be in these very, very, very developing countries, because even, again, the area of developing countries, I mean, the technology is only 20% of the problem. The rest is cultural, societal, education, sustainability, corruption. So for many of these places, all this technology failed, and it's not because of the technology, because they were not able to maintain it. The culture there that you have someone from the West coming, installing everything working. When they leave, the people just cannibalize the plant. They take all the metals, steels, and so on. I will not recommend desalination as a way to solve the water scarcity there. All other options will be much less energy intensive.
Considering that fact that you're saying there is a thermodynamic limit, is it possible that we keep the permeability and increase the selectivity? So it means that that type of separation is not falling in the same plot like Wilson plot. So that separation is going to be a kind of...
So why selectivity is affected?
Because you said the way for the future is to improve the selectivity and keep the permeability as it is, right?
Yeah.
So, and you have that thermodynamic limit, for example, for seawater desalination.
Yeah, but it's independent of the membrane. You assume just independent of the technology. It's just a delta G of separation that you calculate from reversible thermodynamic process. It shouldn't be affected by the type of the membrane, selectivity, and so on. And it's universal for any separation process. You can come up with something that we never thought about it. So it shouldn't affect the energy, the selectivity at all.
Okay, so
it's thermodynamic. It's not affected by this kind of details.
So usually membranes, when you increase the selectivity, usually you lose the permeability. So here you mean that by these processes...
Oh, so it's not the thermo... If you will keep the permeability in the right range, then it will not increase the energy consumption, because I showed you that above a certain permeability, as long as you are above it, you will reach the plateau and the energy will not be improved. If for some reason you increase selectivity and also reduce the water permeability, then you can go to the region that the energy increases. But this water, all the membrane that I suggested will have relatively high permeability, and the focus is that they will remove or reject everything.
So my question is about the semi-batch reactors. Is there a decrease in production as you stop operate at lower pressures and increase it, or is it still the same output through the membrane?
Decrease. Eventually, so we did the simulation that you achieve the same recovery, so the same output.
Well, over per unit time. So does less water come out per unit time initially when you have the lower pressure?
Oh, okay, yeah. So there is some issue there, and this is why to maintain the productivity, you will need to probably have more area, and then you will increase the capital cost. Yeah.
Okay.
Yeah, it's a good point. So the capital cost also because of the increased membrane area that you need, and also the pumps and the stages.
I want to ask about the NOM covering the colloidal particle and the AFM experiment. So the increased repulsive forces that you observed, is it due to the increased hydrophilicity only of the membrane? Was that how you attributed the increase in repulsive forces?
In a way, the way we presented it, when you have a pool of or addition, you usually measure just the stickiness. When we did not see any stickiness, all the curves were just positive, and we reported only the intersection with the y-axis of the value. So it was not really, it's not exactly the repulsion you can measure if you have the approach curve. We did not do it, So it that means that there is no adhesive forces at all.
And the reason was only that the membrane became more hydrophilic.
More hydrophilic, and you have very, very thick hydration layer that prevented the stickiness of this foulant.
All right.
Have time for one more question.
From a student. Only students need to finish. Student? Oh, postdoc is better.
So to follow up actually on the previous question about unit time, with reverse osmosis and the other methods of water purification, is there ever a real problem with the production versus unit time, and do you see that becoming more of a problem, or do you see that becoming more of a problem as we move forward in time and water scarcity is increased?
Production per unit time, flow rate.
So amount of pure water produced per unit time. So that's especially important in, you want to produce enough pure water for everybody in the village, right, or everybody in the city. So making sure that you're meeting that. The way you control it is just by having more membrane area. So you can increase the productivity by having more membrane area. It's not a problem in all these desalination plants. For example, in Israel, they operate nowadays most of the desalination plants only at nighttime because the electricity is half the price. So they don't need even all the water continuously. In California, they built a desalination plant in Santa Barbara in 1994 when I was a faculty at UCLA, I remember, and it's still in standby since 1994. So I don't think there is a problem in getting enough water per unit time. They already built it in a way to get, and they can adjust it the way you want. I guess I'm asking more that would increased permeability, you're saying, that's not going to change energy, but that could change
good question.
Production
so
versus
I did not
unit
say
time.
that. I did not want to jump into it. If you have high water permeability, you're right, you will need much less membrane area. Now, membranes are only 4% of the total cost of desalination. Now, those of you who work with membranes, I don't know how many, it's impossible to work with very, very high water flux. First, if the water flux is very high, you will get intense concentration polarization. Concentration polarization is proportional to the exponential of the water flux over the mass transfer coefficient. Secondly, you get very, very severe fouling. This is why membrane nowadays operate at a certain flux. So you may be able to have maybe not ultra high permeability, but maybe slightly higher, but it will not save a lot of energy there. It will not save enough cost because the membrane are not important part of the cost, and you will get so much fouling, and fouling is critical. This is much more important than all the other things. So,
all right, thank you very much for that talk. And faculty members who are in attendance, if you could stick around for a group picture.